Good morning, everyone. So welcome again to another appointment of the 40U40 lecture series on combustion. It is my great pleasure to introduce today Dr. Alfonso Chinnici. He's a distinguished senior lecturer in sustainability, net zero, and energy innovation at the University of Adelaide, and also is an executive member of the Center of Energy Technology at the same university. The main research interests of Dr. Chinnici are the production application of hydrogen and alternative energy carriers, alongside initiatives that actually targeted decarbonization of carbon-intensive industries, energy networks, transportation systems. His expertise includes heat and mass transfer and reaction engineering, combustion science, solar thermal energy, circular economy practices, and environmentally conscious metal mineral processing techniques. He presently occupies a leadership research role within the Australian Heavy Industry Low Carbon Transition CRC, and in that position he actually closely collaborates with industry leaders to drive net zero initiatives. I really thank you very much, Alfonso, for having accepted our invitation, and I actually give you the word for your lecture.
Great. No, hi everyone, and firstly I would like to thank Salvatore and Alessandro for the kind invitation and for everybody to attend this talk. So as Alessandro mentioned, we'll give you an overview of the work we are doing at the University of Adelaide around different way to tackle the challenge of hard-to-abate sector decarbonization, and of course what's going to be the role of combustion today and in 2030-2050 net zero target. Now, as outline of the talk, firstly I will briefly introduce myself again, my center, and HILT CRC, which funds most of my research these days. Briefly introduce the hard-to-abate sector and the challenge in decarbonizing this sector compared to others. And then I will go through some of the key R&D activity at the university. Most of the talk will be around hydrogen as energy vector, not just in the combustion aspect, but also upstream in the production. And then I will give you just a flavor of the work we are doing, particularly around the iron and steel, but also the alumina decarbonization sector. Now, very briefly, for those who doesn't know me, I basically done my PhD almost 10 years ago now in the group of Mara De Ioannou and Antonio Cavalieri in mild flameless, and then I moved to Adelaide Uni in 2013, and now I serve as a senior lecturer in net zero and sustainability innovation, and also as part of the one of the largest CRC center in Australia. I also serve as the green metals, hydrogen and carbon lead, and within the university center for energy technology I sit on the board executive member of our center. And beside academia, I also work as a consulting for different clients, particularly IEA, but also our both states and federal gov. Now, Adelaide is the capital city of South Australia. For those that never come, I really invite you to come and visit our city. Is quite beautiful, as I would say, being an Italian, Mediterranean kind of climate, very similar to Napoli, as the fourth largest city in Australia. And our university this year is the 150 years anniversary, and we have close to 20,000 students per year from many countries, Southeast Asia, Europe, Australia, US, so from all around the globe. Is quite international city and university. Now, as I say, most of my work sit within the Center for Energy Technology. We call it CET. Is a very multidisciplinary center. Our focus is on net zero industry and also hydrogen. Most of our work starts from fundamental, but has a lot of application. In fact, We do have an industry advisor board that we report to, and the center has been evolved and now is basically a major engine for powering different cooperative research centers in Australia. And today I will talk a little bit more in detail about the HILT CRC. And as you can see from our KPI, besides traditional academic KPI, we have many industry type KPI, particularly in the commercial technology platform. And we just hosted, it finished yesterday, a major industrial high temperature forum, which we host every 2 years. So I really invite you to come to the High Temp 5, which will be in 2026. And in alternative here, we have now grew to a kind of a 300 audience conference on hydrogen production, we call HIPT, which run in alternative years from High Temp. So it would be next year in Adelaide. Now, I've been talking a little bit about HILT CRC, which stands for Heavy Industry Low Carbon Transition. And CRC in Australia stands for Cooperative Research Centre. In the history of CRC, the HILT is one of the largest in terms of both number of partners, but also direct cash funded. It's a 10 years program. It's roughly a 250 million Aussie dollar program, and it's industry managed. We have both independent boards and an external advisor board. And as you can see, we have all the major players as a producer for iron and steel, cement and lime, and alumina sector in Australia. And geographically, typically Australia has majority of the population is around the coast. So you can see from the snapshot of the map, which is basically, we have 6 different industrial hubs, where up west, we have the iron ore hub, which is the biggest in the world. I will show you in my presentation down the track. And southwest and northeast, we have the alumina producer. Now, here is just a snapshot of some, not all of the CRC partners, but as you could probably see from the names, these are the biggest player in iron, steel, cement, and lime, and alumina, such as Alcoa, Liberty GFG, and others. But we also have major technology supply developer, including Combustion, and a series of affiliated associate partners. We have a strong connection with European research center and university, so such as University of Naples, but also DLR in Germany, and up to US with the Arizona State Uni. So it's quite global center in that regard. Now, I've decided to give you a snapshot of the work on the industrial decarbonization only. Of course, we operate at 360 degrees. We look at decarbonization, transport, aviation, fuel, and so on. But for today, I just focus on the hard-to-abate sector. Now, the reason why the center is very focused on decarbonizing heavy industry, you could probably get a flavor of why from these IA plots. Which basically it tells you that while the world is decarbonizing, and we are doing a pretty decent job, I would say, in decarbonizing sectors such as electricity, building, or transport, the industry, particularly the high temperature industrial process, are much harder to decarbonize. And so as the decarbonization goes along over the years, you see that gradually the share of CO2 equivalent that is allocated to the industrial grow to a point that by 2050, the IA is basically telling us that the majority of the share will only come from heavy industry. And the reason for that is because historically heavy industry is a really high capex and a low margin type of sector, but also the technology required to decarbonize is still somehow unproven, to a point that the investors are not happy yet to expose the sector to this kind of low or mid CRL technology. But also most of the, for example, iron or other commodity are exposed to global supply chain, so it's a trade exposed, so which brings additional challenge to the urgency to decarbonize this particular process. Now, of course, this is a challenge, but on the other hand, if you think about the cost of decarbonizing of some big commodities like steel or cement or plastic, with current existing established greener pathway, of course, cost is a problem, is a major concern from the commodity aspect. You see that we are looking up to 20, 30, or even 50% increase on these three commodity price. But when it comes to the end product, the final product, imaging a car or a house or a plastic bottle, the actual potential impact on the final price is quite minor. Minor to a point that it does is sufficiently small enough to potentially drive a premium for production of decarbonized materials. And many early players started to invest in green products just because of the potential impact of utilizing a green premium or other policy mechanism to really fast-track the transition. So this kind of justify further investment, both from a very fundamental R&D up to the actual commercial transition. Now, in terms of additional challenge to a high temperature process for heavy industry, and I believe most of you are familiar with this, I've just listed some key appliances in the iron, steel, cement, and alumina. These are all reactors. They are high temperature, typically above 1,000 for blast furnace. We're also talking about 600 Celsius. So, and also the reactor scale is high. On average, we are looking at 100 megawatt. Now, one of the challenge with current appliance, imagine a blast furnace, is that the lifetime of this reactor technology is around 20, 30 years. This brings really an urgency to decarbonize and really upscale the new emerging pathway to decarbonize this technology. Reason being is that, for example, if you imagine a blast furnace, if today we decide to rely on a blast furnace rather than switching to, for example, DRI process, this will lock in the blast furnace utilization for that particular process for at least another 20 years, given that this is a very high capital intensive relining process. So if we do not provide an alternative to blast furnace or other type of appliance, we are kind of looking for another cycle or lifetime. So we are really pushing out the target that we have for net zero by 2050. Of course, there are many alternative pathways to net zero for this industry. Combustion and hydrogen and derivatives it can, in my view, play a key role. Of course, there are other, I would say, competitors, but not just competitors, also complementary pathway, such as electrification or even using the solar thermal high temperature process. And to some extent, for example, particularly for cement, where you have CO2 coming from limestone, it will make sense to use carbon capture. And depending on availability, biomass can also play a role. Of course, all of these pathways, I'm not going to go into detail today, but they all have different stage of development in terms of TRL, and different opportunity and challenge, but one being a common is relatively high cost. For example, hydrogen is quite, especially the green electrolytic hydrogen is still costly today for some of our partners to really say, yes, let's make a switch to hydrogen today. Now, when it comes to net zero, another things that we really invest in the center is around circularity. So in order to really tackle the challenge of decarbonization heavy industry, we can't think of our process in isolation. And again, this is just a layout of circularity coming from the three major commodities that we have in HILT. And just to give you an idea, for example, lime is a cross commodity, it's been used for many processes in the iron ore sector, but also in the bauxite alumina sector. So decarbonizing one will also means decarbonizing one unlock a transformational opportunity for these other sectors. So again, circularity will play a major role beyond just the technical, combustion challenge or opportunity, in order to really tackle the problem of net zero heavy industry. Now, as I say, of course, we are very active and still in the hydrogen technology aspect. So across all the supply chain, from production, techno-economics of storage and transport, down to the utilization aspect. And today I will try to focus a little bit more about the combustion aspect, given that this is a combustion lecture. But just to give you, set the framework here, if you look at IEA trend for low emission or low carbon hydrogen, you see that roughly we have produced 100 million tons of hydrogen last year, but only less than 1% comes from low emission source. So, and on the other hand, given that majority of the hydrogen comes from oil and gas refining, this is actually a dirty process at the moment. Is actually accounted for close to 3% of global CO2 emission. Now, when it comes to, for example, the IEA pathway to reach net zero, the NZE scenario in IEA, as I say, we are really far away from what we should be, in the sense that currently we only produce 1 million tons per year globally of this low emission hydrogen. What we really should produce is close to 50 million tons per year by not even 6 years from now. So it's really a challenging task, and this really get even higher, close to 65 million tons per year when you look at the 2050. So there are different sources, different technologies being proposed. Of course, the electrolyzer is the key predominant one around the world, but currently is not being scaled up fast enough, and that's mostly because of the high cost of levelized cost of electricity today for many countries around the world. Now, at the University of Adelaide, within our center, we are pretty focused on 3 different alternative production routes beside the electrolyzer. Of course, we do quite a lot of work in electrolyzer, but we are also focused on alternative pathway. One being the what we call ultra green photocatalysis routes, which some of my colleagues in the chemistry department has really done a great job in fast tracking in the last couple of years up to TRL 5 this technology, and they've been backed up by many investors. While my group has been focused more on the thermochemistry side, so we are quite interested in looking at methane or biogas pyrolysis, as well as using alternative source such as solar thermal energy to basically process biomass to produce green syngas. Given the short time today, I would just give you some highlights on why we are interested in methane pyrolysis. Now, when you look at basic of thermodynamics of pyrolysis and you look at comparing that with established electrolysis routes, you see that it makes a lot of sense from a delta H perspective, because it's a third of the energy requirement compared to electrolyzer. And also the amount of, you don't need water, which is another key constraint in many countries around the world for electrolyzers. And also our estimates for current production costs in Australia, but we have many partners around the world that kind of back up this trend also, for example, in US, puts this technology at potentially less than $1 per kg of hydrogen with current established technology production. Now, of the other key interesting point around what we call turquoise hydrogen is that the electricity or the energy source that goes into this reactor to split the methane or the biogas, and the source of the methane is really critical for the CO2 equivalent estimates. You see that in terms of carbon intensity, we could potentially produce a turquoise hydrogen that has negative emission if it's coupled by renewable electricity and, for example, biogas, or very minimum carbon intensity if we use current natural gas. And this is after also included fugitive emission from natural gas operation. So especially in countries such as Australia, where gas is quite cheap and available, it could make quite a lot of sense. Now, we are not trying to reinvent the wheel. There are many companies which we collaborate with around the world that have already quite a lot of advanced, the most advanced being Monolith in US, that's already achieved commercial stage. They use a thermoplasma as their kind of reactor technology. There are a couple of other technology providers, one being Australian, that instead using fluidized bed catalyst and also microwave. At the University of Adelaide, we are now working on instead on what we call molten metal catalysis. So the idea here is to use a molten metal in a bubble flow reactor technology. And you see on the bottom right a schematic of our reactor. On the left side, it's our lab scale reactor, is a 50 kilowatt lab scale reactor, where basically the idea is to have a molten metal. We started with using of tin, but there are also other type of methods that can be utilized, and we bubble gas such as methane or biogas into our bubbling column, and you know, we use resistive heating to produce the heat, and to split at moderate temperature the methane or the natural gas, and basically the carbon floats at the top, while we can recover the unburned methane or the hydrogen product from the top. So this is kind of has a lot of potential advantage because we don't have what we call a sacrificial catalyst. Also, we can take advantage of a high heat and mass transfer coming from public receiver, and also we can tune the residence time of this device to tailor particularly carbon product, which has also strong impact on the techno-economics. We have done quite a lot of work and also modeling of this device, and you see that from a chemical engineering perspective, we have identified that how we produce the bubble is quite critical. Ideally, we would like to produce micro bubble in order to maximize the surface area because of the reaction being mostly dominated at interface. And of course, through the use of Aspen process layout, we have looked at different configuration, and we were able to identify condition where we can obtain high conversion of the methane at relatively low temperature, less than 1000 degrees, which is a step change compared to some of the other processes I've showed before. And cost estimate, we could potentially reach less than $2 Australian dollar per kg, which roughly equate to $1 US per kg. And so we are further investing in this technology with our partner, but we will welcome any collaboration from other research group around the world in this topic, particularly on the kinetic aspect, which is non-trivial. Now, of course, if we have availability of hydrogen at relatively low cost, it makes a lot of sense to utilize hydrogen as a fuel or as a reductant to replace some of the traditional fossil fuel. When it comes to combustion, although hydrogen, it looks like a simple fuel compared to some of the most traditional hydrocarbon, it brings also some challenge. Again, some are listed here, but as you know, there is chance to have higher NOx than traditional hydrocarbon, being of higher adiabatic flame temperature. For process requiring radiation, thinking like rotary kiln in cement and lime, is a major problem because, as you know, hydrogen has a low radiant heat, much lower than hydrocarbon that can produce soot and hence radiation. And also, it's quite a low visibility flame when it comes to hydrogen, which brings a safety aspect in the mix. Also, if you're looking from a blending perspective, this requires technology that can provide fuel flexibility. And back to my initial point around a high cost, we should also start looking in alternative combustion technology, ideally hybrid combustion technology, where we use hydrogen only when it's cheap enough or when there is available stored hydrogen from let's say, imagine from a renewable grid that gets stored and is cheap enough to be used, while in other cases we use more traditional energy source. So in terms of the more fundamental aspect of hydrogen, again, I will try to go quick to this one because I believe most of you are familiar. Of course, we are interested in hydrogen given that it does not produce CO2 when it burns. But when you look, for example, against a methane, properties, chemical, physical properties are quite different. A key one is the energy density of hydrogen. So particularly on a volume base, hydrogen is a third less energy dense than methane. This is a major problem. That's because imagine that you want to push through your burner the exact same amount of heat This means 3 times more volume flow of hydrogen compared to gas to keep the same heat. So you can imagine the challenge in terms of flow rate, velocity, and how we readjust the process performance. And of course, when it comes to laminar flame speed, which, yes, is a critical parameter, as we know, for safety, but it's also a critical parameter that we use today to design our burner. And we know that we have laminar flame speed that is an order of magnitude, as you can see from this video, compared to laminar flame speed of methane. So this really require reconsideration many of current burner, and also bring challenge when you look at retrofit some of the existing appliance, which ideally would be the first stop for our partner when it comes to low risk changes. Now, another interesting plot that I always like to spend few words on is around blending of hydrogen with methane. So if you look in the last 5 years, especially the fundamental level, there are hundreds and hundreds of papers around blending. Is this the right way to decarbonize or to reach net zero? The short answer is no. So if you look from a combustion aspect only, and you look at this plot, basically showing the x-axis the blend of hydrogen and methane by volume, and on the y-axis the actual CO2 reduction. Because of the fact that the hydrogen is actually a third less energy dense than methane, that means that you need to reach at least 80% by volume of hydrogen to only have half of the energy input coming from the blends. So in other words, when we look at blend for net zero, we should only look at the extreme sides of this plot, so 80% and above, which that means it's probably best for us as a combustion community to focus on regenerate burners that basically cope with 100% hydrogen firing, rather than looking at the first step of the blending. Of course, there are other aspects of the supply chain which do make sense to look at blending 5 or 10 or 20% by volume of hydrogen, and this comes more from the gas producer and pipeline operator, where ideally you can pump a little bit of hydrogen in the natural gas to not really decarbonize, in my view, but rather produce momentum in the supply chain in terms of investing in upscaling infrastructure, and also really understand better the whole hydrogen market. But from a very simple combustion perspective, it doesn't make much sense to look at low hydrogen blending for net zero. Now, to this extent, in our group, we are pretty much working hand in hand with many end users. And again, we are lucky enough that our end users are very kind to provide plant data and work hand in hand with our students to really try to tackle this big challenge for their appliance. And particularly with the partner, we are looking at how we can decarbonize with hydrogen, hot gas generator for, I don't know, pelletization, rotary kiln for cement lime, but also reheating steel. All of these appliances has some common feature in terms of challenge, for example, NOx, but others, for example, kill, most specifically around the radiation profile and the radiation fraction, which is challenging with hydrogen. And for reheating steel, you have other additional challenge or constraint where you also need to identify combustion technology that can provide quite uniform and absence of hotspot to avoid reducing the performance of the rolling and the quality of your steel. And the right side of this slide, you can see some of the ideas or technology that we are working on with our partner around both NOx management and radiation improvement. And today I will give you some snapshot of key outcome on that. So just as a start, as an exemplar technology, we are working very closely with the largest pellets producer, pellets producer in the Oceania region. It's a magnetite, pelletized based producer. They use a quite unique way to produce pellets, and they have a series of hot gas generator that today is powered by full-on natural gas. And you see they have a series of roughly 7-8 megawatt register type burner to produce the hot air or hot flue gas needed for the induration step down the track. So we started first looking at understanding what's the challenge or constraint of utilizing existing burner when switched to natural gas, particularly either with a high hydrogen intake in the blend or ideally with 100% hydrogen. And we also look at the series of strategy. Do we need to, for example, optimize the mass airflow rate or rather the equivalence ratio? This is initially it started as a trivia question, but as we show you shortly, it is not. So we have developed a 3D CFD model of their actual commercial plants and burner. We have verified the model through some of our existing pilot plant data that has been provided. Of course, we have done a more in-depth verification of our model training using a lab scale data set that we have in-house. And just to give you a flavor of some of the results, you see on the left side some of the temperature contours and the OH profile within this hot gas generator when we gradually switch from gas to hydrogen. And also what's the impact on the hydrogen intake on components of the burner. And you see that initially this flame, what we call is a flower-like type, so it's relatively short compared to the volume of the hot gas generator. And the flame dynamics stays somehow the same when you move to really high intake of hydrogen, including 100% hydrogen. But you see that when you gradually increase the hydrogen, you start having a flame that is much shorter and much hotter, which, as you can see from the Zwiller temperature here, has a strong impact both on the material lifetime and, as I will show you shortly, on the NOx formation aspect as well. Now, as I said before, you can imagine that much hotter flame will means much hotter NOx, much higher NOx emission. And there is two aspects here. Firstly, one thing that I would like to draw your attention is about how the policy everywhere in EU, US, and also Australia really works against hydrogen utilization today. So today we are bound to report at commercially NOx level as milligram for cubic meter of NOx at dry condition, typically normalized at some oxygen level. But this is not really the right things to do when you start having hydrogen in the mix, because you actually in a biased way bring the limits of hydrogen lower. So actually the right things to do would be to report this as a ENO, as a milligram per megajoule. And few policy mechanisms have been put in place in Australia to change the standards today. So this actually has already been put in place for Type A appliance, and the Type B new policy mechanism on how we report NOx when hydrogen is in the mix will coming in the next few years in Australia. But back to what actually happened in our hot gas generator, you see that keeping the total mass airflow rate does help in keeping the NO low enough even for really high hydrogen intake, while readjusting the equivalence ratio every time we change the fuel has a strong impact on the NOx. But the bottom line of our kind of exercise here is that the current burner does not cope well with 100% hydrogen firing, has really high NOx emission, much higher than existing operation, and really high compared to current limits. So we do need to re-engineerize, redesign the burner to ideally cope with 100% hydrogen firing. Of course, when it comes to coupling the combustion aspect with the process, we still have to remember that at the end of the day, it's not just the combustion, it's also the process. So for example, this particular process, we also need to maintain existing flue gas enthalpy temperature constant or somehow constant while switching between fuels. And this is non-trivial, but again, we have identified that maintaining the mass flow rate constant in our hot gas generator while changing the fuel really does help in preserving both the flue gas temperature and the flue gas enthalpy similar to current gas operation, so that we kind of anticipate only a minor impact on the downstream induration process. But of course, we do need to re-engineerize the burner, and we are doing that quite substantially. Unfortunately, I'm not able to show the actual how we do it, and because of IP commercialization. But just to give you a flavor, you see that we have tried to basically design a ultra low NOx burner suitable for hot gas generator with 100% hydrogen firing, with the least changing to the current operation, and also with the ability to switch between current burner design and the improved burner design for hydrogen whenever hydrogen is available. You see that our prediction in terms of NOx emission brings the burner, even with 100% hydrogen firing, quite low, close to existing operation. So really this has provided sparked a lot of momentum from our investor here in terms of moving to a next step of pilot scale testing of this new burner and hopefully prove the concept at megawatt scale. Now, of course, as you know from our group, we are very strong with fundamental combustion and laser diagnostic. We believe this is always a key to unlock technology developments and further de-risking. So we are working very closely with a key leader in combustion supply developer to really identify new mechanisms to bring NOx down when we operate with 100% hydrogen. So you see here our partners provide a scaled down version of one of their commercial burner to us. This has been 3D printed using additive manufacture, and the mask that you see here from this photo is in titanium. And as you can imagine, this is a scaled down burner version of commercial hot gas generator appliance. Is a non-swirl dual swirl multi-fuel burner, which today is typically used with gas. So we have done a quite detailed campaign using basic, I would say basic characterization of flames from OH star, thermocouple gas analysis, heat flux, and photo. And we are now also moving on more detailed laser diagnostic assessment. But just to give you an idea of what we have identified, and this is kind of a work in progress at the moment, we have operated the flame in between 10 to 100 kilowatts, given or take, with 100% hydrogen flames. And we have identified what we call an M-shape region or high strain mechanism region, which is on the right side of this slide here. So you see that when you move from a relatively low strain to a high strain, the flame gradually moved from a V shape to an M shape. And the M shape is what we are interested in, being as I will show you shortly, a very low NOx mechanism. From a very fundamental point of view, there has been quite a lot of research around M-shape. But what I would say, this is the very first time that this kind of regime has been identified in open flame. So until now, M-shape was mostly identified in confined flame, and flame mechanics behind the establishment of the anchoring of the shape of this M shape was mostly kind of coupled with the presence of a confinement. So we kind of believe this is a new mechanism, and we also utilizing advanced CFD of this lab scale flame, not just for improving our data set for verification of the model at industrial level, but also to really dig down the mechanism behind these high strain 100% hydrogen flames. And when it comes to you see that if we operate the burner with a natural gas, it's quite relatively low NOx. While we need to adjust the strain in the burner to bring the burner to operate in a low NOx regime via an M-shape formation. And again, this is kind of a work in progress, but it's giving us a lot of insight on how we can bring new low NOx mechanisms to reality with our combustion partner. And at the moment, we are basically manufacturing a series of this burner by changing some parameters in the geometry to firstly extend the data set, but also ideally isolate the effect of strain from other, particularly the momentum ratio between the two channels. And if that's successfully, the next step would be to probe the mechanism at scale. So we are thinking about 0.5 megawatt to 1 megawatt kind of pilot scale testing to see if this mechanism still holds at large scale. Now, we are also very active in the second challenge, which is the radiation challenge around hydrogen. As I said before, and as you probably know, hydrogen has very low visibility and has a very low radiation fraction. So when it comes to appliance such as rotary kiln, this is a key problem because the main heat transfer mechanism in rotary kiln is radiation. And also not just the radiation, is the radiation profile that has a strong impact on the final quality of our clinker or our cooked lime. So as per today, bring 100% hydrogen in rotary kiln is almost impossible, very challenging, except if we start identify a way to really change how the radiation coming from hydrogen flames behave in a kiln. So we are identified two kind of mechanisms that could potentially solve or assist in with this challenge. Firstly is in the use of bio-oil doping, and here is a published work from one of my former students 2 years ago from Adam. His PhD was more around doping bio-oil in a pure hydrogen flame. On the left side of this photo is reddish 100% hydrogen flames. And then moving gradually to the right, here you see adding 1, 2, up to 5% by volume of bio-oil. You see that we can basically bring the radiation back to how a natural gas, pure natural gas flame was, actually even higher if we need to. And so we believe that this is potential pathway towards improving both the luminosity of hydrogen, but also closely mimic radiation from hydrocarbon flame. One of the shortcomings identified under tracking this process came from the techno-economics. Bio-oil, of course, is quite expensive. So the selection of a cheap or not refined bio-oil would be a key to further explore this kind of mechanism for radiation improvement in hydrogen flames. Our current focus is still along the side of doping, but we started looking more around using of liquids additives or also particle additives. And today I can show you some work in progress around using hydrogen peroxide as an alternative way of dope hydrogen flames. So for those that are not very familiar with peroxide, we use peroxide today and is readily available in pharmacy. If we have a cut, we can use peroxide for that particular reason. But hydrogen peroxide always come together with water, and depending on the concentration of peroxide in water, we can go from pharmaceutical grade type of peroxide to bleaching. We use a lot for laser cleaning, and up to a monopropellant for our space shuttle rockets. And the reason being is that peroxide goes from a liquid to a phase to a gas phase around 150 degrees Celsius, but at 450 degrees Celsius and under atmospheric pressure release a lot of heat. It's a very exothermic reaction, and it can be seen as an alternative way to produce oxy steam. You see from the reaction, it doesn't go back to hydrogen, but rather to oxygen and to water. So it can be an alternative way to replace air separation units, and also an alternative way to ideally achieve dilute condition close to, for example, mild, which will mitigate NOx while also having some improvement in the radiation. So we have done an early experiment in this area, and we have started doping different grades of peroxide in 100% hydrogen in a quite small needle jet burner that give us quite well confined and well boundary condition that is also important for our CFD modeling. But you see that we have started to identify that the addition of peroxide to 100% hydrogen and the impact of that on the NOx and radiation is non-linear, but overall had a minor impact on flame appearance, but can be seen as both a strong reductant for NOx, but also can bring some improvements in the radiation aspect. Not much like bio-oil, which, because in that particular mechanism we are tailoring the ray radiation from a particulate matter, but this comes more from the infrared from steam. But we believe there could be a strong opportunity here, also in the overall picture of supply chain for hydrogen, giving the peroxide is a derivative for hydrogen. Now, in terms of tackling the other aspects of the cost of hydrogen, and it makes a lot of sense to use hydrogen only when it's cheap enough and when there is enough availability to our end user. So in a few years back, we have started a program around identify novel combustion technology, particularly what we call a hybrid combustion technology. So in short, these are new furnace or new combustor that has the ability to operate both as traditional combustor, but also to bring intake of alternative energy source. One of the focus of that program was around, can we couple a flame together with the concentrated solar energy into the same device? So basically one bucket bringing in multiple energy source simultaneously. And this has a strong advantage. From one end, we are able to stabilize the supply of intermittent renewable energy source, such as solar energy. From the other, also brings a lot of technical benefit. One, when we switch in between energy, the device is hot enough so that we don't have transient or much shorter startup shutdown time. And also the ability to use hydrogen or other alternative fuel only when there is enough and they are cheap enough. And as you can see from the image here, of course, we looked at identify combustion technology that were able to cope well with fuel flexibility while achieving ultra low NOx. So naturally, this kind of pointed to mild flameless combustion as one option. So this technology had a lot of media attention a couple of years ago, particularly from the IES, Solar Peasants magazine, and not just the community, and has brought a lot of scientific paper to our group, but also a lot of new knowledge and insight for the combustion community for the first time on how a combustion environment cope or behave when you have a very different source. Imagine that considered solar thermal is basically radiation and typically has an order of magnitude higher in terms of flux. So on average, a combustion device give you maybe a 0.3 to half megawatt per square meter. When we look at CST, we are easily talking about 3 megawatt per square meter at the peak. So in terms of technicality, there were a few challenges there that we were able to address through appropriate investment in the CFD and the aerodynamic of the 50 kilowatt lab scale device. So in addition to really maximize the recirculation ratio within the reactor, which is a key to establish mild, we also needed to make sure that we had a positive pressure on the aperture. The reason being, this device actually have an opening, and I will show you shortly the device in operation. An opening because we do need basically a hole on aperture to shine or to collect the solar radiation. So this is kind of a very complex problem because we basically have a combustor at 1200 Celsius, and suddenly you have a hole in it, and you can imagine you don't want your hot gas coming out. So the aerodynamic side aspect was quite critical. We needed to make sure that either we had a natural plane at the aperture, or we end up having actually slightly intake of cold ambient air into the device through a suction maximum of high speed inclined jet that create the recirculation. But when it comes to the experimental aspects, the fact that we selected mild and we did a good job in the aerodynamic and the upstream aspect of the design really paid well in terms of showing that we can preserve the same thermal efficiency or heat extraction efficiency regardless of the modes. So we have 3 modes here. We can basically operate the furnace as it is, so we can close the aperture if there is no sun. We call it combustion only mode. We can have the 2 energy source at the same time. We call mixed mode. And if there is enough sun, we don't need the combustion aspect, so we basically shut off the fuel from our nozzle and we only operate this as a solar collector. But this has shown that we can deliver similar performance, and also we can operate this with pure hydrogen and also with syngas from very, I would say, low grade to high grade syngas without having much penalty on the efficiency, and also mild kind of take care of the having, you know, single digit NOx. So this was quite successful for our group, and also Again, just to give you an idea of what I'm talking about here is a snapshot of our furnace that was operating with pure hydrogen at 1200 Celsius. You see that the aperture is right in the middle, so there is no window there. Is that you can actually put your hand inside, and we were crazy enough to take a couple of photos very close to the burner, but we really believe in our CFD model. In fact, it was cold in the sense that we were able to have some cold entry of ambient air rather than basically having hot gas coming out. And here you see our one of our solar simulators. This is a kind of an old one that we use that was going to be aligned to the aperture in order to start the mixed modes of operation. So in terms of where we are in technology development here, the TRL that we reached in 3 years of program was roughly TRL 5. We provide a lot of new insight on mild solar hydrogen and syngas process, but also more importantly, the design for the mild furnace only was then spin-off to another study for a commercial Brazilian iron ore pelletizer through CFD, given that there was a strong fuel flexibility and low NOx performance from that work. Now, our group through the HILT is quite focused at the moment in decarbonizing the iron steel. The reason being is that for those that are not familiar with the iron and the steel supply chain around the world, firstly, and I always like to set the scene by showing this slide. When you think about the metals that we mine today, roughly we mine roughly 3.5 billion tons of material every year. 95% of this is iron ore. So you can think about lithium, aluminium, copper, whatever. That's only 5% of what we mine today. 95% is iron ore. And by far, Australia is the biggest producer today. We produce almost 1 billion. We export 1 billion ton of iron ore to our countries such as China, Korea, India, EU, and Japan. So Australia, if you think about it, you look at the steel that is in your house and office, that means that on average, there is 1 in 2 chance that the steel that is in there comes from an Australian iron ore. And while the scope 1 and 2 emission of Australia is relatively small for iron ore, we are by far the biggest problem for us is the scope 3 emission, given that the steel making makes up 7 to 9% of the global CO2 equivalent emission. So these are huge numbers, almost impossible if you never visited a mine to see how big an operation of an iron ore producer looks like. So, of course, this is just starting from the scale, this is a big challenge. But compared to other green metals or pathway, for the iron and steel making, hydrogen is, I would say, is the most prospective net zero reductant and fuel. And that's been kind of an established pathway for hydrogen. Reason being, is a very good reductant as intermediate for producing green steel from green iron without, of course, producing or emitting carbon. And again, if you are familiar with the iron steel pathway, there are plenty out there of studies and pathway to reach or to produce green steel within the net zero target that we have globally. But most of them, it pop-ups the words hydrogen and coupling green hydrogen DRI with an electric arc furnace. So hydrogen has a key role to play, of course. Cost and availability and supply chain is still kind of a barrier for that. Now, one of the things, of course, Australia is very strong in the upstream aspects in terms of the mining of, side of the iron ore, is that people don't realize that we are almost at a turning stone. We have a big problem. We've been mining iron ore for many years. And while there are many emerging green energy tech to produce green steel, this green steel tech do require really high grades of iron ore, while the low-grade iron ore in Australia is depleting very, very fast. So we really have a problem that we do, before we move into green tech for steel, we need new technology to clean up our iron ore and basically achieve a grade that's suitable as a feedstock for, a DRI EAF kind of pathway or similar. So in Australia, this is called beneficiation, but it's a kind of a loose term that basically is a category where you can think all the process for cleaning the minerals, concentrate it, bring to the grade that is needed for further processing. Now, at University of Adelaide, through the HILT, we have patents couple of technology that could potentially solve the challenge of low-grade iron ore. And this is all around basically providing high flux radiation. So as you see from the slide, what we are suggesting is to have a thermal pretreatment done in a very smart way to concentrate and clean up some of this low-grade iron prior to substream down, recovering a further concentrated using, for example, grinding or magnetic separation. And in this context, we are, of course, working with our end user, particularly with an Italian-based company, actually is a global leader in conveyor belts. It's called Magaldi. They also have a branch in the green thermal storage aspect. But for this particular program, we kind of join force in basically design a novel conveyor belt that can operate with high flux radiation coming from bespoke hydrogen burners, but also concentrated solar thermal or resistive heating, and of course hybrids of those. Back to my previous slide around the needs for hybridization. And the idea is to basically heat treated some of this low-grade iron in an engineered way, so that we can induce chemical physical changes to the material that is more amenable to upgrading and also more amenable to downstream green steel making process. So combustion is still a key for some of these emerging pathway here. Again, we are very lucky to work with many end users around the world that provide us different type of low-grade iron ore. Again, I'm not going to do the detail of the mineralogy today, but how the ore behaves is really depending on the initial property of this ore. Here you see a snapshot of our bespoke premixed hydrogen high flux radiation burner. It's basically a surface combustion type of burner that can provide a high flux radiation. Typically, these operate in the order of 0.3 megawatt per square meter at the surface, roughly 1,000 degrees, and heating rates in between 10 to 200 Celsius per second. We can adjust the heating rate of the temperature by basically adjusting the relative distance between the bed of material and the high flux radiant heating source. Now, I will probably go quick to some of these slides, but basically, we first start looking in, can we use hydrogen or similar radiant heating source to induce big thermal stress to the rocks so that we soften up the ore so that we can much easier grind this ore. Reason being is that grinding alone, and that's something I learned, coming from Europe to Australia first time, I was really aware how much energy goes in a grinding or combination circuit. Just to give you a number, 3% of the electricity produced today goes in grinding all around the world. So it's a huge number. So if we can even save a point digit of that, we actually making a big impact. So we were able to show to our partners on average that we can reduce the grinding energy following this novel hydrogen or radiant heat treatment, close to 20% reduction. So it's quite a large number. Of course, the mineralogy has an effect on the absolute value of reduction on the grinding energy. And here you can see a snapshot of why this is happening. So you see this big thermal stress creating big cracking. And of course, we are also using calcination on some of the iron content, which helps bringing the steam out from this rock that basically promotes this cracking further. When it comes to actual cleaning precondition of the ore, we're able to show that from a low-grade iron ore, which we can't sell it today, anything less than 57% iron by mass is not sellable, has not economic value today. But we were able to show that we could bring it to a 60-65% Fe concentrate, 62 being current market specs, 65 will go for a green premium, particularly for a DRI. So this has a lot of course, attention by our partner investor, but globally has also impact on the hydrogen supply chain with this novel technology. At the more fundamental level, we were also able to show that if we use hydrogen and we use high flux radiation, we can really change the way how the ore responds to heat treatment. We can, on average, bring much higher surface area to the ore, which has a strong impact on downstream process, such as for the separation, but also in further reduction aspects prior to making green steel. And also, again, at the fundamental level, and in my view, coming from a combustion, more traditional combustion community, this has also strong impact for our combustion community. We are rethinking the way how calcination regime operates by simply change the type of combustion that we utilize to calcine iron, but not just iron. We have done similar work in magnesite, limestone, and different type of minerals. You see that basically the flash heating using this high flux has a strong impact on the conversion, the time needed for conversion, and the temperature at which conversion happen. Plus has a strong impact on the chemical physical change that we can basically induce to some of these powders. So this has unlocked a lot of opportunity for really making a step change in the performance of this upstream technology. Of course, our partner, at the end of the day, the dollar value is the dollar value. It doesn't make sense from a point of view. So our group is also strong in bottom-up techno-economic estimates. And again, story short for these slides is that while, of course, hydrogen is still more expensive today than the gas, on average, the levelized cost of beneficiation plus loading this ore and the freights load to China or Japan is in the order $10 to $12 per ton, which is much, much lower than both current and future price for iron. So there is still a healthy gap in terms of potential net profit for our iron ore producer here, which basically unlock further investment in technology, de-risking, upscaling, and demonstration down the track in our program. As everything in research, things sometimes happen in a more serendipitous way. So our high flux radiation method, as I showed you before, was mostly taught as a preconditioning or cleaning of mineral ores. But we started realizing that this can also be used for tailings from different industrial waste. And that's not just for Australian waste, is also applicable from many EU or US type of waste that require some sort of thermal pretreatment in order to be more prone to liberate key ions such as Fe, magnesium, calcium that can be utilized in alternative carbon capture utilization storage methods such as mineral carbonation in order to basically permanently store in a benign solid form our CO2 that can come from other direct air capture methods up to a flue gas or more concentrated CO2 stream. So we were able to preliminarily show, and we were very quick in patents and upscaling the theory of this new activation methods of waste with the same basically methodology of how we do beneficiation with high flux radiation, high flux coming from other hydrogen or other similar source. And on average, you see this is a paper that will appear soon on fuels where we were able to improve the magnesium extraction from our industrial waste by almost a factor of 2 compared to establish commercial rotary kiln for doing basically the same job in heat treatment of serpentine. And this basically means almost doubling the carbonation capacity or carbonation potential of our waste. So this also has unlocked quite lots of attention from different potential partner for us. Now, as I saw at the beginning of the HILT, we not only work with end user, but also with many technology developers. So we are work very closely with Calex. Calex is a global company, has a commercial magnesite plant in US, but has also a strong presence at pre-commercial high TRL R&D level in Europe and in Australia. Towards basically utilizing an alternative calcination reduction technology for many big commodity. In Australia, you see here the pilot scale plant that they have close to Melbourne is a roughly 20-meter tall drop tube is an indirectly heated tubular reactor. The idea here is to basically drop from the top iron ore fines that get heated through this indirect tube, and while they drop down to the tube, the hydrogen is injected from the bottom, and the hydrogen here acts as a reductant. So as a key product from this process, you have direct reduction hydrogen, DRI, that can be used either directly charge the electrical furnace or transform in HBI for export. And while from the top, you will recycle any excess hydrogen, and also you have quite a lot of steam that can be reutilized for producing combined heat and power. Now, we work very closely with them, not just on the demonstration aspect, but also how we can further improve the understanding of the technology, which is, I would say, at the lower TRL compared to more established type of way of how we do today reduction, mostly being shaft furnace, but also fluidized bed type. And together with them, the Calex team has demonstrated a lot of benefit in using this novel chemi-reactor drop tube type technology for Fe reduction. So on average, they were able to show that they can achieve really high metallization degree from different type of ore, but also potentially reduce the temperature which reductions are happening. So this could potentially bring a lot of benefit in terms of energy requirement for a DRI step. Now, our role in that, of course, in supporting them in pilot scale demonstration was also in trying to further the understanding of the fundamental of the process. And we have tackled that in a three way. One, through basically a traditional process approach. Second and third being advanced CFD machine learning, which I will show you shortly, and also laser diagnostic. Now, from the kind of a process point of view, we basically reimagine this drop tube as a series of perfect stereo reactor. So we have, divide the reactor in a couple of zones. And again, the powder comes from the top, the hydrogen is injected from the bottom. And here you see the different temperature gradient that you can achieve by preserving basically the energy that comes from the electrical heater through the wall. We have identified a series of kinetic models. So we have tested the most established kinetic model for iron ore reduction. It comes from literature. We have done some fine-tuning in-house because, of course, all of these models were developed for lab scale and also for a slightly different condition compared to the drop tube from the Calex team. And here you see a snapshot of the Aspen model that basically is able to tell us two things. One is the fractional conversion in each of the zone, and also the total conversion in a DRI. Here you see basically a snapshot of our model, and on the left side you see the measured and modeled conversion, so the total metallization degree. You see that both kinetic model that we select after fine-tuning do a pretty decent job in predicting the trend of the experimental data. While what is kind of a challenge and also an opportunity from a very fundamental R&D perspective is the fractional conversion along the height of the tube, where the two models basically predict inverse trend. So basically very different conversion history despite having a similar final conversion. So from a combustion kind of community point of view, this means there is more work required for us to better understand the reduction kinetics for iron, but also we do need to provide a better understanding through in situ experimental data of the controlling parameter, including residence time, the temperature, and the conversion. So we have tried, or we are trying to do that in different way. As you know, our team is very strong in laser diagnostic. This is a work that is led by my colleague Ziwei Sun, and so we have basically developed novel optical diagnostic methods. They are quite relatively cheap and simple to develop for our partner, but able to provide more in situ understanding of basically potential for agglomeration and also in situ particle velocity. But also we are pretty focused on improving the model prediction from particle dispersion model from low fidelity URANs, and we are doing that through basically using physically informed deep learning coupled in our CFD. Again, I will skip through some of this complexity of the DL CFD framework, but there is the reference from the paper. But basically, on average, you see that through slightly increase only 1.2 times the time needed for baseline URANs through basically coupling with deep learning from physically informed analysis, we are able to improve basically most of the parameters coming from URANs prediction, from eddy viscosity kind of fields, the fluid velocity fields, and also, of course, the particle dispersion and particle velocity fields. So happy to maybe chat offline on this if somebody is more interested on the detail. Of course, we are very strong in alumina, and alumina is all around us in our iPhone everywhere. So aluminium will stay with us for quite some time. It's a critical minerals for panel and wind turbine production. And again, in Europe, the focus is more on the aluminium. Australia is the biggest producer of alumina, which is the precursor for aluminium, and also is by far the biggest emitter of CO2 for us, because you're looking at roughly 200 pegajoule of energy by only 6 refineries for alumina in Australia. So again, here we believe that, especially for the calcination combustion, will play a big role, especially if transition to hydrogen and oxy-hydrogen kind of environment. And having, of course, hydrogen in the mix will not only impact the combustion performance, but actually the aluminum calcination process. And we believe that through the use of steam enrichment, we are able to show that we can also improve the quality of smelter grade alumina while reducing overall the calcination temperature. And again, this has a strong impact on the energy requirement, but also on the quality of what we can produce with the alumina refining of tomorrow. But of course, we do need to, retrofit or re-engineerize our flash calciner or CFB. We have a couple of PhD students working on the impact of hydrogen from a combustion perspective on both flash and modeling of circulating fluidized bed for alumina. So as a final remarks, and sorry, I was a little bit long, but we believe that combustion science is still critical to many of the both established and emerging technology pathway to accelerate the decarbonization heavy industry, and not just decarbonization, also a transformation. And some of the skills that we learn or we have from our more traditional combustion community are directly and also indirectly applicable for development of this novel reactor. CFD, machine learning, laser-based being, to me, still quite critical to unlocking the fundamental understanding needed for the risking upscaling. Probably I'll stop there, but again, thanks everyone for listening. And we at the University of Adelaide always welcome opportunity to strengthen the collaboration and hosting PhD postdoc anytime. Thank you, everybody, and happy to take any question. I'll probably stop sharing here.
Okay, thanks a lot, Alfonso. Thank you for this very dense and technology-oriented, I will say, presentation. So yeah, the floor is open for questions. So if anyone from the audience would like to ask a question, please feel free to unmute yourself and ask.
Hello.
Yeah, Pratibha, go ahead.
Hi. Yeah, hi. Thanks for the really very informative presentation. I have quite a lot of questions, but I'll mostly focus on the radiation improvement part. So there you have mentioned that bio-oil doping is improving radiation, but can bio-oil doping improve radiation without causing issues in flame stability or efficiency?
So thanks for the question. Of course, so from our work, we have showed, our work is mostly done on other swirl or black body types of flames, which are simplified from commercial flames. And bio-oil doping, so far, the flame stability wasn't much of a concern for us, to be honest. Actually, the flame dynamics again, I must say that the doping was done not a really high intake, and the reason being we did not want to kill the techno-economics of the process. So we are looking at 1 to 2% by volume of the bio oil in hydrogen flames, and all the work so far has shown not much impact on flame dynamics. Potentially that could become a challenge at a much higher blending or doping value.
Okay, and at that percentage, is it causing any hotspot or non-uniform temperature distribution if you are studying anything like that?
Yeah, no, so yeah, we have done quite a lot of work also on the fundamental of that. Again, bio oil will improve radiation mostly through, I would say, more traditional soot mechanism or particle re-radiation mechanism. So to translate that from fundamental in the lab to commercial, one thing we are working on is on where the injection is. So is it best to inject that from a fuel side, from an oxidant side, or having a separate injection from the doping? That is actually critical towards more, having a practical doping mechanism for our industrial burner.
Okay, yeah, and you are mostly focusing on the particle size, like radiation inside the gas part, right?
So the bio oil will produce basically particle radiation. Of course, then the part will be reoxidized. So typically following a mechanism in the kiln. We are now more focused on additives, just because bio oil it's actually quite expensive solution. So although technically it's feasible, the economics were not promising. Our key focus at the moment is using other, peroxide as a liquid additive or solid particle doping, which unfortunately I can't tell you much at the moment because of IP reason, but that's where we are actually aiming at the moment.
Okay, just the last one. Have you done any modeling work on the radiation part? Because I understand in addition to the radiation modeling, the spectral properties of the gases is going to be a challenge to look into.
Yeah, no, that definitely is a challenge. We did not release any paper yet on that, but we have 2 CFD postdocs at the moment modeling that particular aspect, and I would say it's quite challenging. So that could be a good opportunity to maybe have some collaboration with other group. It's quite interesting aspect, but also challenging at the same time.
Yeah, thank you so much for answering the questions.
Thank you, Pratibha. Are there any other questions from the audience? If not at the moment, Alessandro had to leave for a meeting, but he left me two questions to ask you, if you don't mind. One is, how do you place mild flameless combustion as a technology in the decarbonization route?
That very good question, Salvador. And probably, have you seen from the slide, I've tried not to talk much about mild because maybe the community knows a lot about the work we do in mild dilute combustion in Adelaide over the years. So mild has a lot of opportunity. So again, we know that it's fuel flexible. We know has low NOx, but I would say from industrial perspective, there is quite a lot of barrier for certain applications. So for example, again, in a rotary kiln, it would be almost impractical, impossible to have a mild flameless mode. That's because of the specific non-uniform radiation profile that you have to add to a kiln in order to achieve the product quality for the clinker. While of course, the most natural and also in flash calciner could bring some additional challenge. So at the moment, we are focusing on mild flames in existing more traditional applications such as recuperative, regenerative furnace, which it's state of the art industrially. We are looking in exploring mild in again multi-phase flash calciner, so like pre-calciner or flash calciner for alumina, which traditionally has not been done with mild, but naturally, if you look at how a flash calciner look like, you have high preheating of air, of an oxidant, you have strong swirl intensity because it's almost a cyclone, but of course, you need to make sure that And we know from a mild perspective, we need to be above self-ignition, and not just by a bit, but quite a few hundred degrees to make sure the turn down ratio of this appliance stay in a stable mode. But we believe, and we are investing quite a lot on R&D there, that can be extended to multi-phase flash calciner, which is something that's not been out there, or current flash calciner do not operate in mild as such, although naturally they could be fine-tuned to that. There are other applications, especially in the alumina, that mild could be applicable. The glass industry could have some application for mild flameless. Reheating steel is a bit of a question mark at the moment, in the sense that Europe is leading the way there. If you're looking at greenfield reheating steel, for example, you have Linde that has already quite a lot of oxy steam. That's called mild-like opportunity. But when you look at retrofitting reheating steel, it's quite hard to achieve mild. So, but not impossible. So, it really needs to be looked at case by case. That's kind of my view.
But yeah, lots of potential. And another question, final question, if there are any other questions from the audience, will be that you showed us that we have a huge need of H2 and there are different routes also to produce H2 and use it. And what is your opinion? I mean, can we reach the target put by the net zero target that you showed in one of your slides, or we need then a combination of routes? And I mean, also what is, in your opinion, the role of ammonia, since you haven't talked about it, and I was curious to know if it's one rather feasible route or there are other options available. Thank you.
Now, thanks for these two comments. So firstly, and actually we were hosting quite a lot of C-suite and government people just this week in our high temp. My view around net zero targets and where we are with hydrogen, how much hydrogen would be needed, and is it actually another hype, and then we may not reach that. To me, that's not the right question. Can we achieve the net zero target? Because it's a transformational journey. Without having target in place, all this slow machine will not happen. So without having targets in place, very unlikely, especially very conservative, high capex, heavy industry will not start investing in that. So do we have enough hydrogen, or is that trajectory looks promising for hydrogen supply chain? I would say no, but things are happening, and especially from both from a bit more involved in policy mechanism and some of the COP kind of direction, both in EU and Australia. So really favoring some mechanisms to basically cope with the high cost of hydrogen. So having some governments basically provide some share of the price to try and bring it to the $1 or $2 kg, which looks like a magic number. But again, to me, it's all about transformation of the technology and pathway, which is happening. If hydrogen is going to be the primary, it's yet to be understood. There are other alternative, electrification, use of biomass derived fuels, concentrated solar thermal, that's another option, and a mix of those. Your second comments was about maybe if you just remind me, the second point was
ammonia. What's the role if what you think?
Yes. So we don't do much ammonia yet in our group. Mostly is a geopolitical reason, because hydrogen. So Australia is kind of placed itself as a renewable superpower and ideally a potential key country for hydrogen production, given that we have abundant solar energy, wind, and other renewables. But given that if we are going to produce hydrogen domestically, it makes more sense to basically consume hydrogen on site without having to go through all the other transformation for ammonia. So when it comes to ammonia, when my work with IE a while back was around supply chain of ammonia to Japan and Australia, Ammonia makes a lot of sense when, for example, you want to transport hydrogen across many kilometers, so especially let's say Australia to EU, Australia to Japan. But in that case, the ammonia challenge in combustion or maybe cracking, it comes to the end user. So we see that especially for our partner, being ammonia as a kind of a secondary impact rather than a primary R&D work in Australia. But of course, we do a little bit on, especially on the thermal pre-cracking of ammonia, coupled with mild flames, but they're mostly a gas turbine appliance rather than, that's the work I do with Paul Medwell and Michael Evans, but that's not for heavy industry, it's more like for transportation, decarbonization. But again, we are very happy to collaborate in ammonia. I personally believe it has a strong potential to decarbonize and also really offer a way to safely and relatively cheaply transport ammonia, hydrogen across the globe.
Okay, thank you very much. I think we can conclude the Q&A session. I can set you free for the weekend and for your evening. And I would like to thank you again for your very informative, like as it was said before, talk. And I want to thank you everyone for their participation and see you at the next appointment of the 40 under 40. And I would like to thank again our speaker. Thanks a lot, Alfonso. It was a pleasure.
Thank you, Salvador. Thank you, everybody, for listening. Again, feel free to reach out to me for any other, other questions or comments that you have, or for potential collaboration. We're always happy to collaborate in this field. Thank you, Salvador, again. Alessandro.
Bye. Have a nice weekend.
Bye, everyone.
Bye.